Hello everybody, and today we're going to be talking about taking roots and rational exponents. So we've got a few definitions that we need to talk about, and I think you guys probably already know this, so we're just going to kind of get through this pretty quick, hopefully. So our first definition there says if n is an even positive integer, the nth root of a non-negative real number a is that unique non-negative real number denoted by the nth root of a, such that the nth root of a raised to the n power equals a. So when n equals 2, we write the square root of a as just the square root, so we don't have to put the 2 there. So that's the first thing, is that if you don't see a number, that means we're taking the square root. And that's something that you guys have all worked with already. Now, you start getting into higher n values for our roots, we have to pay attention to a few things. So notice the fourth root of 81 here is 3, because that means, moving things around, because that means that it takes 4 3's to multiply together to give us 81. So like the sixth root of 64 would be 2, because it takes 6 2's to multiply together to give you 64. Something else that you guys have talked about is in Algebra 1, Algebra 2 probably, you can't take the square root of a negative number. It gives you a non-real result. You might remember complex numbers or imaginary numbers from your Algebra 2 class. So if we had something like the fourth root of negative 81, there's no solution there either. There's no real solution. So this leads us to our next definition, that whenever we have a negative underneath an even root, it's always going to be no real solution. Can't do it. And a good way to remember that is if you forget and you type it in your calculator will say error. All right. So the next definition here we have is if n is an odd positive integer greater than 1, the nth root of the real number a is that unique real number denoted by the nth root of a. Math definitions are never fun. But what that's telling us is that if we have an odd root, we can have negative numbers underneath there. So if we look at the next sentence here, notice we got the cube root of negative 8. And that equals negative 2, because negative 2 times negative 2 times negative 2 does equal negative 8. Like the fifth root of 32, negative 32 is negative 2. So again, negative 2 multiplied by itself 5 times will give us the negative 32. So even roots, if there's a negative, no real solution. Odd roots, if there's a negative underneath the radical, you can solve them. So next thing that hopefully you've seen before, I know in Algebra 2 we do touch on this a little bit. We can write radicals with rational exponents. So this is your definition here, and keep it as simple as possible. All that's saying is that if we have the square root of something or nth root of something, we can rewrite that using rational exponents. So like the square root of 5, right? I could rewrite that if I wanted to as 5 to the 1/2 power, because remember that's implied that there's a 2 there. So that's all it means. So you can rewrite them. You take the root and you put it in the bottom of the fraction. That's all there is to it. So you might also have exponents as well, and that's just adding on this right here. So if you look at this, if we had, let's say, x to the 4th, and let's take the third root, the cube root of it. So if I wanted to rewrite this, what I could do is just put x to the 4 over 3. So the exponent goes on top and the root goes on bottom. Not too bad, right? And in the first section of this chapter, we talked about the laws of exponents and what we could do with them. Those all hold true for rational exponents as well. So this is one of the benefits of using rational exponents, is that it makes it easier to do multiply, divide, radicals, because we can just use the laws of exponents. All right, so, oh wow, so I used square root. All right, so we got x squared and then taking the fifth root. So we want to write each expression in radical form as an expression in exponential form, and then each expression in exponential form as an expression in radical form. I'm having a hard time talking today. So all we have to do here is say, all right, our exponent is a 2. Our root is a 5. So x to the 2/5. Pretty straightforward, right? Now with this guy, we have here. Couldn't we, that's a square root, right? So we'd have x to the 3/2 power. Now, not too bad, right? So 3 to the 4/7. So that means we're going to have a 3 underneath our radical. And what the root we're taking is the 7th root, so there should be a 7 right there. And then to the 4th power, that is an exponent. Another way you could write this would be like this. You could put the 4 on the outside if you wanted to. A lot of people put parentheses when they write it like that. All right, 5 to the negative 2/3. Well, let's go ahead and deal with that. So the negative is telling us that we need to be in our denominator. We need to move it down. And then we're going to have our radical. We got a 5 here to the 2nd power, and we're taking the cube root. So now we just need to simplify these things. So with this guy, we got to figure out what times itself 3 times equals 125. Hopefully, you're thinking 5. Let's go ahead and take a look at this. So 5 times 25, right? Then 25 is 5 times 5. So you see how we have 3 5s? So another way you kind of think about this, I'm going to write it out a couple different ways. So if we could think of it like that, and well, that would just leave us with a 5, right? Another way you could think of it with rational exponents would be, well, 5 to the 3/3, right? And doesn't that just reduce the 1? So that gives you 5 too. So kind of look at them with the rational exponents. It might make them a little bit easier to solve. I don't know, whatever you prefer. So b here, we got the 5th root of 1/32. So what we're going to do here is factor 32, get the prime factorization and see what we got. So what, 2 and 16, 16 is 2 and 8, 8 is 2 and 4, and 4 is 2 and 2, right? So that leaves us with 1, 2, 3, 4, 5 2s. So what we have here would be the 5th root of 1/2 to the 5th, right? Notice now we're able to reduce this. Well, the 5th root of 1 is just 1, and then the 5th root of 2 to the 5th is 2. So we'd be left with 1/2. All right, so now with this guy, we can keep it in the rational exponent form, or we can write it in the radicals if you prefer. You know, it's up to you. So I'm going to take a look at this, and what this is telling us is that we need to raise the 9 to the 3rd power, and we got to take the square root of it. So I'm just going to do this in my head here, but I think it's pretty easy. If you can take the root first, I would totally tell you to do the root first. So the square root of 9 would be 3. So be left with 3 to the 3rd power now. And well, 3 to the 3rd, 3 times 3 times 3 is 27. Not bad, right? So this next one here, we've got negative 8/27 raised to the 2/3 power. So again, you want to think about it. Well, my radical kind of ran off the screen there, but this will be raised to the 2nd power and the 3rd root, right? So I'm going to do the same thing again. I'm going to say, what is the cube root of a negative 8? Well, negative 2 times negative 2 times negative 2, right? So we keep our negative there. So that's a 2. There's the cube root all over. The cube root of 27, well, that would be a 3, because 3 times 3 times 3 is 27. Now we still have to square everything. So now when we square it, negative 2/3 times negative 2/3, well, that's going to give us positive 4/9, and we are done. All right, so now this one has variables in it. And this kind of throws people through a loop sometime, but it's not that bad. So we're just going to kind of work our way through it and see what we got. All right, so notice with A, we got to do the cube root. So I'm going to break apart 32 and see what I have here. what do we have? 2 times 16. 16 is 2 times 8. 8 is 2 times 4. And 4 is 2 times 2. So let's see how many groups of 3 we have. There's 1, and we only have 2 2's left. So we know that we can put a 2 on the outside because of that group of 3. So this tells us that we can pull 1 2 out, and that the other 2 2's need to stay inside the radical. So I'm going to color those green just to help us remember all this. So the next thing we want to do here is deal with this x to the 6th. I think it's way easier to think of it as a rational exponent because, well, what's 6 divided by 3? 2, right? So that means we're going to have an x squared on the outside because we can pull that out. And then y to the 17th. Wow. How many times is... Think about it this way. How many times does it go in it evenly? And you guys tell me 5, right? So that would be y to the 15 thirds. And well, what's left over? Y to the 2 thirds, right? Using those rules of our exponents, notice that adds up to 17 thirds. So now we would have, what is 15 over 3 reduced to? Y to the 5th. So we're able to pull that y to the 5th out as well. So let me get everything color coded. So this will be on the outside. This has to stay in the inside, the y squared, because we don't have three of them. And then the x squared can come out. So let's write our answer out. So we've got a 2 on the outside, y to the, well, let's do our x first, x squared, y to the 5th, and then inside of our cube root, we still have 2 times 2, which is 4. Oh, I just screwed up all the coloring. My bad. And then y to the 2nd. So 2x squared, y to the 5th, times the cube root of 4y squared. A lot of work, but it's not too bad, right? All right, so let me erase all this. So I have plenty of room. And let's do the next one. So this next example, we're taking the cube root of. Now, we got to find the cube root of 81. Doesn't sound that fun, does it? It's not bad. We're going to kind of look at it the same way. So I'm going to put 81 over here. And let's just break it apart. It's 3 times 27. 27 is 3 times 9. 9 is 3 times 3, right? So that means I'm going to get the colors right this time. We can pull out 1 3 because we have 3 of them, but we have to leave that 3 inside the radical. So let's move on to the x. So if we look at our x to the 13th, think of it as rational exponent. How many times does that go in there? Well, it would go in 4 times, right? That would give us 12 over 3, and we have 1 left over. So 12 thirds would reduce to x to the 4th. So again, we're able to keep that. We can pull that out. Let me get the colors right. We're able to pull out the x to the 4th, and the x to the 1st power is going to have to stay inside the cube root. Now, y to the 21st. Well, this one's going to be pretty easy, right? 21 divided by 3 is 7. So that works out nice and neat, and we're able to pull that one out as well. So that'll be yellow. So our solution, our simplified solution would look like, well, we got a 3 we can put on the outside, an x to the 4th, and then y to the 7th. And then we have our cube root, and we put back what we can't get out, one of the 3's and an x to the 1st power, and that would be our answer. 3x to the 4th, y to the 7th times the cube root of 3x. All right, so let's do our next problem here. 5th root. Now, more than likely, you're not going to see a whole lot of these. The cube root will be handy, I think, in the real world, but things above the cube root, you probably won't see too much. Well, let's go ahead and break this guy apart. Well, 18, x to the 18th, that would be 18 over 5, right? Well, that means 5 goes in 18 3 times, so that would make 15 fifths. And then we would have x to the 3/5 left over. So that means this would reduce to x cubed. So we could pull that guy out. So that one comes out, and the x to the third is going to have to stay inside the radical. So let's deal with this 32. So I'm going to do the prime factorization of 32 just to see what it is. 2 times 16. 16 is 2 times 8. 8 is 2 times 4. 4 is 2 times 2. So that gives us 1, 2, 3, 4, 5 2's. So we're able, so the 5th root of 32 is 2. So we're able to get that out. All right, so we have an x cubed on the outside, all over 2 on the outside, and then we have our 5th root of x cubed, and that would be our solution.